Welcome back, wonderful people. This is Mr. Ndabezita, and we are continuing with our RL circuit. In this time, we will just look at the problems that are being provided for us and see whether we can apply our previous knowledge of the first tutorial in industrial electronics to try and solve the problems that we have. Now we have a problem with me here, and let me just switch on this laptop. They say to us a coil of inductance 3 Henry and a resistor of resistance 700 ohm are connected to a 200 volt 50 hertz supply, and they want us to calculate a few things. Now before we can calculate a few things, there are a few questions that we need to ask ourselves. The first one is the circuit connected in series, or is this circuit connected in parallel, so that I know the type of a connection that I am dealing with. Now, since we spoke about the RL circuit that was connected in series, and we never spoke about anything that is connected in parallel, so this RL circuit is a series connected kind of a circuit. So now let us try to deal with this. Now, how are we going to do this? Now, remember they said a coil of inductance 3 Henry and a resistance of 700 ohm is connected to a 200 volts 50 hertz AC supply. Okay, let us try to draw the series RL circuit for this. So this would be the resistor, and this would be the inductor. They are connected in series on an alternating source of 200 volts 50 hertz. So this, we will do this to depict that it is a coil, an inductor, and this one, it's a resistor of 700 ohm and an inductor of 3 Henry. Okay, so what is it that I want to do here? Now the first question, they say that we should calculate the inductive reactance of the coil, meaning the resistance of the coil, meaning the amount of resistance the coil has, meaning we are calculating how much value is opposing the flow of current, because that's what resistance does. It stands as a barrier to the flow of current. So the inductive reactance XL, it's given by the formula 2 pi FL, and we dealt with this with you wonderful people. We already dealt with this. All right, and then from there I can take my 2 pi, because it is a constant, it is a number, and I can take the value of the frequency as 50, and I can multiply this by the value of the inductor, which is 3 Henry. And when you punch all this into the calculator, I think we will come up with a certain value. And let me just do this very quickly. 2 pi is the same as 360 multiplied by 50 multiplied by 3. And I will find a value of how much? 2 pi FL, and I find a value of 54,000. This is the value that I find if I use 360, not 2 pi. But let me use 2 pi and see if there will be any difference. So I will come here and say 2 pi. And when I use 2 pi, I find 300 pi, which is equal to 942.478 ohm. So this is what I find. So please, when you are here, do not say 360. It's true that this is the radian measure. This is in radians. And if you convert radians, you make this a degree, because 2 pi equals 360. You're going to get some very serious problem there. So please do not change this to 360. Rather use that 2 pi. Okay, this is one thing that I wanted to show you. But I'm glad that we have seen that. So we get 942.478, and we are very much fine. And this is the resistance, the amount of resistance that stands as a barrier to the flow of current. Okay, that was number A. We go to number B, the impedance of the coil. This is what they are looking for. And I know that the impedance of the coil is the total resistance of the circuit. And then via the phasor diagrams, I saw that the impedance is found using the theorem of Pythagoras. So that is to say, Z, which is the total resistance of the circuit, it's R squared plus XL squared. R is 700 squared, 942.478. That is also squared. Okay, and punching in our calculators, we will find a value of 1173.995 degrees. And what is this? This is the total opposition to the flow of current, right? We found XL to be 942, and we found we were provided with the value of the resistor as 700, and the impedance is 1173. So this value is bigger than this value, and also bigger than the inductive reactance. So that tells you that the total resistance of the circuit has increased. Why? Because this is in a series circuit. The voltage is the same, but the current flowing is the same, but the resistance of the circuit increases in a series circuit. So meaning, in a series circuit, if the total resistance of the circuit increases, that will bring about a decrease in current, because they are of inverse proportion with one another, provided that the voltage stays the same. All right, let's go to number C. And they say that we should find the value of the current through the coil, through the inductor. But I know that the current that flows in the resistor is the same current that will flow in the inductor, and it is the same current that will flow in our source. So this is the total current, basically what I'm looking for. And I can apply Ohm's law for this, because the total current is equals to total voltage divided by total resistance, which is equals to Vt divided by Z, because Z is in fact the total resistance of the circuit, the impedance of the circuit. And this will be 200 volts divided by 1173.995, and we should find a current that is flowing in the circuit as 0.170 amperes. Okay, this is the amount of current that is flowing in the circuit. All right, number D, find the phase angle between the supply voltage and the supply current. Right, what is it that I know? I know a phasor diagram that tells me this is the voltage across the inductor, and this is the voltage across the resistor, and this is the current. And I can see that the voltage of the inductor and the voltage of the resistor lags one another by a specific amount of angle there. So they lag one another. So meaning there is a phase angle there. Okay. And another phasor diagram will tell me that if I have XL here, because I've already calculated XL, and I have the value of R here, and I have the value of current, this will be the Z there, as much as here I will have my V total and the angle that is formed with the x-axis. Okay, so instead of using this, I can use this to find the phase angle. Why this and not that? I don't have the voltage across the inductor. I did not calculate that. I don't have the voltage across the resistor. I didn't calculate that. But with this one, I already have the inductive reactance. I already have the value of the resistor, and I also have the impedance. So I can work with this one. So I know that the tangent of theta is equals to the opposite over adjacent, which is y over x. So y over x. And theta will be arctan of XL divided by R. And we find opposite over adjacent, okay, which should give us a value of what? I can substitute the value for XL, which is 942.478, and the value of R is 700. And I will find a value of 1.346. That is the 10. Sorry, this is the 10 of theta. And arc10 of this value will be equals to 53.390 degrees. So this is the phase angle between the supply voltage and the supply current. Alternatively, somebody can say the cosine of theta is equals to adjacent over the hypotenuse. Okay, so the cosine of theta will be the adjacent, which is the value of R, over the hypotenuse, which is the value of Z. Okay, so that theta would be arc cos of R over Z, which is equal, let's come here, arc cos of R, the value is 700, divided by Z, 1173.995, and we would find a value of what? 53.416, and you round off this, you will get 5.4 degrees. So this is the phase angle between the supply voltage and the current. And the last question, they say draw the impedance diagram. So the impedance diagram, we have already done that. The impedance diagram will be drawn in terms of what was being calculated. We calculated XL, we calculated the impedance, and we calculated the current. So you'll have your XL, you'll have your R, you'll have your I, and you will have your Z. and you will have your phase angle there of 53.416 degrees. So you can insert the values there if you want. That is fine. You can also show us the values of the current. And this is one problem that I wanted us to look at, so that it wraps up everything that we talked of in the first tutorial. So thank you for watching, guys, and I will see you in the next tutorial. Do not forget to share, like, and subscribe to the fundamentals of Ndabezit.